Hello there. Welcome to the Science Owl Station channel. Today we journey gently toward a quiet red light in the night sky, a distant world that has watched humanity for thousands of years, glowing softly like an ember in the vast dark. Right now, as you listen, perhaps Mars is somewhere above you. Maybe it hangs low near the horizon, or perhaps it is hidden beyond the curve of the Earth. Imagine stepping outside into cool evening air. The sky is deep blue fading into black, and among the steady stars there is one point that does not twinkle quite the same way. It shines with a faint copper hue. Steady, patient, ancient. That is Mars. Before we drift further, if you enjoy calm explorations like this, consider subscribing and letting this channel accompany your quieter evenings. And I would love to know, where are you listening from tonight and what time is it there? Is it late and still, or early morning with soft light touching your window? Leave a comment and let me imagine the gentle world around you. Mars has always felt close to us, not only in distance but in imagination. It is our neighbor, the fourth planet from the Sun, orbiting just beyond Earth. Of all the planets in the solar system, it is the one that has stirred the most intimate questions. Not as crushing and hostile as Venus, not as distant and gaseous as Jupiter. Mars sits in a middle place, almost familiar, almost reachable. When ancient astronomers looked up, they noticed its unusual color. While most stars shimmered white or blue, Mars burned faintly red. Its hue evoked blood, fire, iron. To the Romans, this reddish wanderer became associated with their god of war, Mars, a name that carried both power and unease. The Greeks had called it Ares before them. Across cultures, that reddish spark seemed to whisper of conflict, heat, and restless energy. Yet there is something ironic in that association. For when we study Mars closely, it is not a raging battlefield we find, but a quiet desert, a cold, silent world where winds sweep across plains of dust, where mountains stand taller than any on Earth, and where time itself seems to move with patient slowness. I often imagine what it would feel like to stand there. The sky would not be blue but butterscotch, tinted by fine dust suspended in a thin atmosphere. The sun would appear smaller, less intense, casting long shadows across a landscape of rust-colored stone. The ground beneath your boots would be dry, brittle, ancient. No birds, no oceans, just the whisper of wind moving through empty space. And yet, for all its silence, Mars holds stories. It holds evidence of flowing water in the distant past, rivers that once carved valleys, lakes that once shimmered under a warmer sky. It holds frozen caps of ice at its poles, layered like pages of a history book written in frost and dust. This duality, desolate yet promising, barren yet once active, is what keeps our curiosity alive. Mars is not merely a red dot. It is a question about life beyond Earth, a question about our future as a species, a question about how planets change, cool, and age. In this exploration, we will move slowly. At first, we will uncover some of its most astonishing features. Mountains that dwarf Everest, canyons that stretch farther than imagination, storms that can envelop the entire planet. And then, gradually, we will settle into softer observations. The rhythm of its orbit, the quiet drift of dust across its plains, the almost meditative rotation of a world turning beneath a pale sun. For now, Just let yourself hold the image of that small red glow. It is not merely distant rock. It is a mirror of Earth's possible futures and pasts. It is a reminder that worlds can change, that climates can shift, that oceans can vanish, and that curiosity, gentle, persistent curiosity, is what carries us outward. Wherever you are, let the world slow down for a while. Soften your gaze, let the hum of life around you fade, and gently drift with us into tonight's quiet exploration. And as we begin, keep that red ember in mind, steady and patient in the darkness, waiting for us to understand it just a little more. When we lift our eyes from Earth and trace the orderly paths of the planets, Mars appears as the fourth world from the Sun, a quiet traveler circling just beyond our own orbit. If you imagine the solar system as a widening ripple with the Sun glowing warmly at the center, then Mercury is the innermost flicker, Venus the bright and clouded lantern, Earth our blue and breathing home, and then, just a little farther out, comes Mars. Its orbit lies at an average distance of about 228 million kilometers from the Sun. That may sound immense, and it is, yet in cosmic terms it is still part of our inner planetary neighborhood. When Mars and Earth align on the same side of the Sun during what astronomers call opposition, the distance between us can shrink to roughly 56 million kilometers. At such times, Mars shines especially bright in our sky, its reddish hue deepening, as if it has drawn a little closer to share its quiet secrets. The name Mars carries ancient weight. The Romans looked up and saw a color that reminded them of iron and blood, and they named the wandering star after their god of war. To them, Mars was fierce and strong, a divine embodiment of battle and courage. Earlier still, the Greeks had associated it with Ares, a similar figure of conflict and raw force. Across centuries and civilizations, that red tint seemed to stir something instinctive in the human imagination, something primal and powerful. Yet what fascinates me is how a simple color shaped so much mythology. The redness of Mars does not come from fire or violence, but from iron oxide, essentially rust, coating its surface. The planet is wrapped in a fine dust of oxidized iron particles. In sunlight, this dust scatters light in such a way that the entire globe takes on that warm, coppery tone. It is less a symbol of war and more a testament to chemistry, to the quiet reactions between rock and oxygen over immense spans of time. And still, for thousands of years, Mars seemed alive in another way. In the late 19th and early 20th centuries, telescopic observations led some astronomers to believe they saw straight lines crisscrossing its surface. These were called canals, and for a time, many people imagined they were artificial, built by an advanced civilization struggling to distribute water across a drying world. Newspapers printed illustrations. Writers crafted elaborate stories. Mars became not just a planet, but a possible home for intelligent life. Though we now understand that those canals were optical illusions, patterns created by the human eye trying to impose order on blurry images, the fascination they sparked never truly faded. Instead, it transformed. Rather than imagining vast Martian cities, scientists began asking quieter questions. Could simple life exist there? Did water once flow freely? Could Mars have once been warmer, wetter, more Earth-like? Perhaps what draws us most strongly is that Mars feels familiar in shape and rhythm. It has polar ice caps like Earth. It has seasons, shifting subtly as the planet tilts on its axis. It has clouds, dust storms, and the faint whisper of wind. It is not a gas giant without solid ground. It is not an icy dwarf far beyond sunlight's warmth. It is a rocky world, a sibling in some ways that evolved differently. When I think about humanity's fascination with Mars, I see a thread that stretches from ancient skywatchers to modern robotic explorers. In Babylonian records, in Roman myths, in Renaissance sketches, and now in high-resolution satellite imagery, Mars has always been present, a constant red companion in our cultural memory. There is also something intimate in its scale. Mars is smaller than Earth, about half our planet's diameter. Feels reachable, not close enough to touch easily, but not impossibly distant either. It invites the imagination to stretch just far enough to be daring, but not so far as to be lost. And perhaps beneath all the science, beneath the equations and spacecraft and instruments, there remains a simple human longing, the desire to know whether we are alone. Mars, with its ancient riverbeds and frozen poles, stands as a quiet candidate in that search. Not because it promises easy answers, but because it once had conditions that might have allowed something fragile and microscopic to emerge. As we continue, we will explore its measurements, its gravity, its days and years. But for now, just hold this thought. For millennia, a small red light has stirred myths of gods and battles, dreams of civilizations, and questions about life itself. It turns slowly in the dark, unhurried, as it always has. If we could gently hold Mars beside Earth, not in reality but in imagination, we would notice first its size. It is smaller, distinctly so, yet not insignificant. Mars has a diameter of about 6,779 kilometers, while Earth stretches nearly twice as wide at roughly 12,742 kilometers. In simple terms, Mars is about half the diameter of our planet. If Earth were the size of a large apple resting in your palm, Mars would be more like a plum, rounded, solid, but clearly more modest in scale. Because of this smaller size, its mass is also far less. Mars contains only about 10% of Earth's mass. This difference shapes everything about the planet, from its gravity to its ability to hold onto an atmosphere. Gravity on Mars is about 38% of what you feel standing on Earth. If you weigh 70 kilograms here, you would weigh the equivalent of about 26 or 27 kilograms there. I like to imagine what that would feel like. Each step would be lighter, slower, almost dreamlike. You would not float away, but you would move in long, graceful arcs. A small jump would carry you farther. Dust would rise softly beneath your boots and fall back gently in the thin air. Even simple motion would feel slightly delayed, as though time itself had stretched just a little wider. That lower gravity, however, has deeper consequences. Over billions of years, Mars' weaker gravitational pull made it more difficult for the planet to retain a thick atmosphere. Lighter gases escaped into space. Without a dense atmospheric blanket to trap heat, the planet gradually cooled. The warmth that once may have allowed rivers to flow slowly faded. In this quiet interplay between size and gravity, we begin to see how subtle differences can shape an entire world's destiny. Mars orbits the Sun at an average distance of about 228 million kilometers, roughly 1.5 times the distance between Earth and the Sun. Because it sits farther out, sunlight reaching Mars is weaker, only about 43% as intense as what bathes our planet. The Sun would still shine brightly if you stood there, but it would appear smaller in the sky, a more distant lamp casting a softer glow. This increased distance affects temperature profoundly. With less solar energy and a thin atmosphere, Mars struggles to hold onto warmth. Its average surface temperature hovers around -60 degrees Celsius. In equatorial regions during midday, temperatures can briefly climb to around 20 degrees Celsius, almost comfortable. But at night, the heat escapes quickly, plunging back down into deep cold. There is something almost poetic about these contrasts. A world that can briefly warm under the sun, then surrender entirely to the chill of space. A planet that seems to inhale faint warmth during the day and exhale it completely by night. Despite its smaller size, Mars still bears the hallmarks of a rocky terrestrial planet. It has a crust, a mantle, and a core. Its core is believed to be composed primarily of iron, nickel, and sulfur, though it is smaller and cooler than Earth's molten interior. Without a strong global magnetic field like Earth's, Mars lost one of its great shields against solar wind. Charged particles streaming from the sun gradually stripped away much of its atmosphere over immense stretches of time. And yet, in all these numbers, diameter, mass, gravity, distance, there is something steady and calming. Mars follows predictable paths. Its measurements are not chaotic. They are precise, measured, almost meditative in their consistency. When we compare Mars and Earth, we see not a failure, not a lesser world, but a variation. A sibling shaped by slightly different starting conditions. A planet that began similarly with volcanoes, water, atmosphere, and then drifted along a cooler, quieter evolutionary path. In its smaller scale lies both vulnerability and beauty. It is a reminder that planetary fates hinge on delicate balances. A bit more mass, a bit more gravity, a slightly stronger magnetic field, and history might have unfolded differently. For now, let us simply rest with these proportions. Half the size, 1/10 the mass, gravity at 38%, sunlight softened by distance, a smaller world, turning patiently in its wider orbit. If we now follow Mars along its path around the Sun, we begin to notice the rhythm of its motion. Steady, deliberate, unhurried. A full journey around the Sun, what we would call a year, takes Mars about 687 Earth days, nearly twice as long as our own year. If you were keeping a calendar there, you would wait almost 2 Earth years to celebrate a single Martian birthday. This longer year is a simple consequence of distance. The farther a planet orbits from the Sun, the wider its path, and the slower it must travel to remain bound by gravity. Mars moves at an average orbital speed of about 24 kilometers per second, slightly slower than Earth's 30 kilometers per second. It is not a dramatic difference, yet over time it stretches the year into something noticeably longer, like a quiet extension of seasons. And seasons do exist there. Mars is tilted on its axis by about 25 degrees, remarkably similar to Earth's 23.5-degree tilt. Because of this gentle lean, sunlight strikes different hemispheres more directly at different times of the Martian year, creating seasonal cycles. There are Martian springs, summers, autumns, and winters, but these seasons unfold differently. Since the year is longer, each season lasts nearly twice as long as those on Earth. Imagine a winter that lingers for many months, stretching across time with cold patience, or a summer that unfolds slowly, gradually warming the dusty plains before easing back into chill once more. There is another subtle difference. Mars' orbit is more elliptical, more stretched than Earth's nearly circular path. This means that the distance between Mars and the Sun changes more noticeably throughout the year. When Mars is closest to the Sun, a point called perihelion, its southern hemisphere experiences shorter but slightly warmer summers. When it swings farther away at aphelion, the northern hemisphere endures longer, cooler summers. The imbalance creates a delicate asymmetry between hemispheres, a quiet planetary variation. Now let us slow even further and consider the length of a single day. A Martian day, called a sol, lasts about 24 hours and 39 minutes. That is astonishingly close to Earth's 24-hour rotation. If you were standing on Mars, your sense of daily rhythm might feel strangely familiar. Sunrise, midday, sunset, the cadence would echo home, only extended by a gentle 40 minutes. Scientists who operate robotic rovers on Mars sometimes adjust their own schedules to match the Martian sol. They work slightly longer days, shifting their sleep patterns gradually, living in step with another planet's rotation. I find that thought comforting, that somewhere on Earth, people align their circadian rhythms to a world millions of kilometers away, synchronizing themselves with a distant sunrise. When dawn breaks on Mars, the sun rises more slowly through a thin atmosphere tinted with dust. The sky, often a soft butterscotch hue during the day, can turn bluish near the sun at sunset, the opposite of Earth's red sunsets. Fine particles in the air scatter light differently, creating delicate color inversions. Twilight lingers quietly across the plains, shadows stretching long and thin. Because the atmosphere is so sparse, temperatures shift dramatically between day and night. The planet cannot hold onto heat effectively. As the sun dips below the horizon, warmth radiates quickly back into space. The surface cools rapidly, and frost may form in certain regions, settling briefly before the next morning's light. Everything about Mars' motion feels measured. The long year, the slightly extended day, the gradual turning of seasons. It is not a frantic world. It does not rush. Its orbit traces the same path again and again, guided by gravity, steady as breath. If you imagine watching Mars from a distance, you would see a small globe rotating with calm precision, circling its star in a predictable dance. There is comfort in that predictability, in knowing that even across millions of kilometers, there is order. A sol passes, another follows. A year stretches nearly twice as long. Seasons lean gently back and forth with the tilt of its axis. And through it all, the red planet continues its patient revolution, turning quietly beneath a smaller sun. If we now descend from the quiet mechanics of orbit and rotation, and let our imagination settle gently onto the surface, we begin to see why Mars glows with that unmistakable red. It is not fire that colors the land, nor molten rivers of lava flowing endlessly across its plains. The redness comes from iron, ancient iron, locked within rocks and dust, slowly reacting with oxygen over immense stretches of time. Iron oxide, rust, the same process that stains an old nail left in rain has painted an entire planet in shades of copper and ochre. Over billions of years, fine particles of oxidized iron have been ground down by impacts, fractured by temperature shifts, and carried by wind into a powder so delicate that it can remain suspended in the thin atmosphere. When sunlight touches this dust, it scatters in such a way that Mars appears warm and red, even from millions of kilometers away. Up close, the surface is more varied than a single color suggests. There are tones of brown, muted gold, deep crimson, and even pale tan. Some regions are darker basaltic plains, remnants of ancient lava flows. Others are lighter, dust-covered expanses that stretch toward the horizon in quiet monotony. The terrain itself is astonishingly diverse. Mars is not a flat desert world. It is sculpted by volcanoes, by tectonic forces long stilled, by impacts from asteroids, and by the subtle erosion of wind. Vast volcanic provinces rise gently above surrounding plains. Broad valleys carve their way across the crust. Impact craters dot the landscape, some sharp-edged and young, others softened by the slow accumulation of dust. One of the most intriguing features of the Martian surface is the stark difference between its northern and southern hemispheres. The southern hemisphere is dominated by highlands, ancient, heavily cratered terrain that stands several kilometers higher on average than the north. These highlands are rugged and old, their surfaces preserving scars from impacts billions of years ago. In contrast, the northern hemisphere is largely composed of low-lying plains. These regions are smoother, less densely cratered, and appear younger. Some scientists believe that in the distant past, these northern lowlands may have held vast bodies of water, perhaps even an ocean that covered a significant portion of the hemisphere. The idea is quiet and speculative, but compelling. A shallow sea reflecting a pale sun, waves lapping gently against ancient shores. Between the highlands and lowlands lies a dramatic boundary. Not a single line, but a complex transition zone that hints at powerful geological events in the planet's early history. Whether caused by massive impacts or internal processes within the crust, this dichotomy remains one of Mars' enduring mysteries. Wind plays an important role in shaping the present surface. Though the atmosphere is thin, less than 1% of Earth's atmospheric pressure, it is still capable of movement. When winds rise, they lift fine dust and carry it across plains and into the sky. Over time, dunes form, graceful ripples of sand-like material that migrate slowly, reshaped grain by grain. These dunes can be found in crater basins and along the edges of ancient valleys, arranged in delicate patterns that speak of persistent though gentle forces. The soil itself, called regolith, is dry and granular. It is composed of broken rock fragments, volcanic material, and oxidized minerals. There is no living organic layer as we know it on Earth, no roots binding particles together, no worms or microbes churning the ground. It is mineral and silent. Yet beneath this quiet exterior lies a record of immense change. There are channels that resemble dried riverbeds, their curves too fluid and intricate to have been carved by anything but flowing liquid. There are deltas and fan-shaped deposits at the mouths of ancient valleys. These shapes suggest that Mars was not always the frozen desert we see today. Standing there, if one could, you would see a horizon tinted by dust, broken occasionally by distant ridges or crater rims. The ground would crunch softly underfoot. The sky above would glow faintly amber. And beneath that sky, the planet would appear both barren and beautiful, a canvas of geological time painted in rust. The more we look, the more we realize that Mars' red color is not merely a surface trait. It is the visual expression of its history, a reminder that chemistry, atmosphere, and time collaborate patiently. Iron meets oxygen, Dust rises and settles. Highlands tower quietly in the south while low plains stretch across the north. A world of contrasts, wrapped in a thin veil of red. If we continue wandering across this rust-colored landscape, letting our gaze drift toward the horizon, there is a place where the ground begins to rise. Slowly at first, almost imperceptibly, and then more boldly until it forms the largest volcano in the entire solar system. Its name is Olympus Mons. Olympus Mons is not simply tall. It is immense in a way that is difficult to fully imagine. It rises about 22 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. If you could place Everest at its base, it would appear modest, almost restrained. Olympus Mons stretches upward with a broad, shield-like profile, its slopes gentle and expansive rather than steep and jagged. But height is only part of the story. The volcano spans roughly 600 kilometers across, about the size of France. Its base is so wide that if you stood upon its slopes, you might not even realize you were climbing a mountain. The curvature of Mars would hide the summit from view. The incline is gradual, like a slow upward drift of land rather than a dramatic peak piercing the sky. Olympus Mons is what scientists call a shield volcano, formed by repeated flows of low-viscosity lava spreading outward over long periods of time. Unlike explosive volcanoes on Earth that build steep cones, shield volcanoes create broad, dome structures. On Mars, without active plate tectonics to shift the crust beneath it, a volcanic hotspot could remain in one place for millions of years, allowing lava to accumulate in layer upon layer, growing ever taller and wider. Earth's crust is divided into moving plates, and as they shift, volcanic hotspots migrate relative to the surface. But Mars does not appear to have this same dynamic plate system. Its crust is more static. So when magma rose from the mantle beneath Olympus Mons, it continued erupting in roughly the same location for an extended span of time. The result is a volcano of extraordinary scale, a monument to persistence. At the summit lies a vast caldera, a collapsed crater formed after enormous volumes of magma drained away. In fact, Olympus Mons has multiple overlapping calderas, evidence of successive episodes of eruption and collapse. If you could hover above it, you would see a layered crown of depressions, each marking a chapter in the volcano's history. Around its base runs a steep escarpment, cliffs that drop several kilometers to the surrounding plains. These cliffs likely formed as lava flows accumulated and the weight of the volcano caused the crust beneath it to sink slightly. Landslides may have shaped portions of its flanks, creating ridges and debris fields that extend outward. And yet, despite its size, Olympus Mons rests in silence. There are no glowing lava rivers today, no ash clouds rising into the sky. The volcano is considered dormant or extinct. It stands as a relic of a more geologically active past, a time when Mars' interior was warmer, when molten rock surged upward more frequently. I sometimes imagine standing somewhere along its slope. The ground would tilt gently beneath your feet. The sky above would appear faintly hazy with suspended dust. The summit would lie far beyond visible reach, hidden by the curvature of the planet. There would be no vegetation, no birds circling overhead, only vast stillness and the quiet acknowledgement that you are on the largest volcano known. The scale of Olympus Mons reminds us how planetary conditions influence geology. Mars' lower gravity allows volcanic structures to grow taller before collapsing under their own weight. Its lack of plate tectonics allows hotspots to build mountains without drifting away. Subtle differences, gravity, crust movement, internal heat, combine to produce something extraordinary. And as we continue our slow exploration, Olympus Mons becomes not merely a geological feature, but a symbol of accumulation over time, layer upon layer of lava spreading patiently outward, growth measured not in moments but in millions of years, a mountain so broad it bends with the planet's curve, a summit so high it rises into thinner air still, and beneath it all, a quiet world that once burned more brightly within. If Olympus Mons rises as a monument to upward force, then Valles Marineris stretches in the opposite direction. A vast scar drawn across the surface, a canyon system so immense that it reshapes our sense of scale. Valles Marineris extends for about 4,000 kilometers along the Martian equator. To place that into perspective, it would span nearly the entire width of the continental United States. If laid across Europe, it would stretch from Portugal to well beyond the Ural Mountains. It is not a single canyon, but a complex network of chasms, valleys, and fractured terrain, interwoven like deep folds in the crust of the planet. At its widest points, Valles Marineris reaches up to 200 kilometers across. Its depth can plunge as much as 7 kilometers below the surrounding plains, several times deeper than Earth's Grand Canyon. In fact, compared to the Grand Canyon, Valles Marineris is more than 10 times longer, far wider, and significantly deeper. When spacecraft first transmitted detailed images of this region, scientists were astonished. The scale defied expectation. From orbit, the canyon appears as a dark ribbon cutting across the planet's rusty surface, casting long shadows that emphasize its depth. Unlike river-carved canyons on Earth, Valles Marineris is believed to have formed primarily through tectonic processes, stretching and cracking of the crust. As nearby volcanic regions, including the immense Tharsis volcanic plateau, swelled upward due to internal forces, the crust around them may have fractured under tension. These fractures widened over time, creating deep troughs. Gravity then took over. Sections of canyon walls collapsed inward. Landslides tumbled downward in massive cascades of rock and debris. The interior became a layered landscape of fallen material, terraces, and ridges. In some regions, there is evidence that water may once have flowed through portions of the canyon, leaving behind mineral deposits that hint at a wetter past. Imagine standing at the rim of such a canyon. The ground beneath you ends abruptly, giving way to a vast chasm descending into shadow. The air would be thin and cold. The sky overhead would glow faintly amber. Across the abyss, distant walls would rise in layered bands of rock, reds, browns, muted grays, each layer a record of ancient geological time. Light would fall differently here. In the early morning, the canyon floor might remain in darkness while the upper rims catch the first sunlight. As the day progresses, shadows would shift slowly along the walls, emphasizing their height and texture. The sense of depth would be immense, yet silent. No echo of rushing rivers, no vegetation clinging to the rock. Only wind, faint and intermittent. There are regions within Valles Marineris where strange mounds and chaotic terrain appear, jumbled blocks of crust that seem to have collapsed and shifted unpredictably. Scientists call some of these areas chaos regions, suggesting past interactions between subsurface ice, groundwater, and tectonic stress. Perhaps pockets of ice melted and destabilized the ground above. Perhaps underground water once seeped and drained away, leaving cavities that later collapsed. As with Olympus Mons, the canyon reflects the unique planetary conditions of Mars. Lower gravity allows for taller cliffs before structural failure. The absence of active plate tectonics means fractures can remain preserved for billions of years. With minimal erosion from rain or flowing rivers in the present era, these features endure largely unchanged, their sharp outlines etched clearly against time. Valles Marineris is not a place of movement today. It is a place of stillness, of suspended history. Yet its formation speaks of immense internal forces, of crust stretching, cracking, shifting. A reminder that even a quiet planet once experienced powerful geological transformation. When we look at images of this canyon from orbit, it resembles a wound. But it is not a wound in pain, it is a record, a geological memory of tension and release, preserved in rock and shadow. A canyon longer than continents, deeper than familiar valleys, wide enough that from one side, the opposite rim can appear distant and hazy. And yet, beneath that vastness, there is only wind moving softly across ancient stone. If we lift ourselves now from the canyon floor and rise gently upward, above cliffs and plains and volcanoes, we enter the thin and fragile envelope that surrounds Mars, its atmosphere. Compared to Earth's rich and protective blanket of air, the Martian atmosphere is delicate, almost ghost-like. It is composed primarily of carbon dioxide, about 95%, with smaller amounts of argon and nitrogen. There are traces of oxygen, water vapor, and other gases, but only in minute quantities. If you could stand on the surface without protection, which of course you could not safely do, you would find the air far too thin to breathe. The atmospheric pressure at the surface averages about 6 millibars. On Earth, at sea level, atmospheric pressure is about 1,013 millibars. That means Mars' surface pressure is less than 1% of Earth's. This difference changes everything. With such low pressure, liquid water cannot remain stable for long on the surface. It would either freeze quickly in the cold temperatures or boil away into vapor because of the reduced pressure, sometimes both processes occurring almost simultaneously. Water, if present in liquid form, is fleeting. The thinness of the atmosphere also means that Mars has little protection against incoming radiation. On Earth, our dense atmosphere and global magnetic field shield us from much of the sun's energetic particles and cosmic radiation. Mars, lacking a strong global magnetic field and possessing only a sparse atmospheric layer, receives higher levels of radiation at its surface. Over billions of years, this radiation and the solar wind have gradually stripped away much of what may once have been a thicker atmosphere. And yet, though thin, the Martian atmosphere is not entirely still. It moves. Winds arise, carrying fine dust across plains and into the sky. The atmosphere may be light, but it is active enough to shape dunes and lift particles high above the surface. When sunlight passes through this atmosphere, it behaves differently than it does on Earth. The sky often appears a soft yellowish or butterscotch hue during the day due to dust suspended in the air. At sunset, something remarkable happens. Instead of glowing red as on Earth, the sky near the sun can appear bluish. Fine dust particles scatter red light more effectively, allowing blue light to dominate in the region directly around the setting sun. It is a quiet inversion of what we are used to, a subtle reminder that familiar processes can produce unfamiliar beauty under different conditions. Clouds do exist on Mars, though they are delicate and often composed of ice crystals. Thin wisps of water ice clouds can drift high in the atmosphere. In colder seasons, carbon dioxide itself can condense into frost and even snow near the poles. These clouds are faint, ethereal, barely visible against the dusty sky. Yet they confirm that even a thin atmosphere can sustain cycles of condensation and sublimation. Because the atmosphere holds so little heat, temperatures fluctuate widely. During the day, sunlight may warm the ground, but at night, that warmth radiates quickly back into space. There is no thick atmospheric layer to trap it. The result is a world of sharp thermal contrasts. Warmth in sunlight, biting cold in shadow. Standing there, the air would not feel like wind against your skin in the way it does on Earth. It would be lighter, more subtle. A breeze might move dust in gentle curtains across the surface, but it would lack the dense force of terrestrial gusts. The sound, too, would be muted. Sound waves travel differently in thin air. Voices would carry weakly. The world would feel hushed. In this fragile atmosphere, we see a delicate balance. Enough gas to form clouds and stir winds, yet too little to shield, to warm, to sustain liquid water freely. It is a reminder of how atmospheres shape habitability. A small difference in mass, a small change in magnetic protection, and the envelope of air can thin over time, altering the destiny of a planet. Carbon dioxide dominates. Argon and nitrogen linger in smaller amounts. Pressure remains faint, barely pressing upon the surface. Above the red plains and towering volcanoes, this subtle layer drifts and circulates, thin, restless, and quietly shaping the world below. Within that thin atmosphere, light as it is, weather still unfolds. It is quieter than Earth's weather, less humid, less dynamic in the way we are accustomed to. Yet it exists, shaped by dust, sunlight, and seasonal change. The average surface temperature on Mars rests around -60 degrees Celsius. That number, simple and steady, masks a wide range. Near the equator during midday in summer, temperatures can rise briefly to about 20 degrees Celsius, mild enough, in theory, for liquid water to exist if pressure allowed it. But as soon as the sun lowers, the warmth dissipates quickly. Night can bring temperatures plunging to -80 degrees Celsius or lower. Near the poles in winter, it can drop below -120 degrees Celsius. This dramatic swing between day and night occurs because of the thin atmosphere's limited ability to retain heat. Mars absorbs sunlight and releases it almost as quickly. Warmth is a passing visitor, never lingering long after dusk. Perhaps the most remarkable aspect of Martian weather is its dust. The planet's surface is coated in fine, iron-rich particles, easily lifted by wind. Though the atmosphere is thin, it is capable of sustaining powerful dust storms. Some are local, swirling columns of dust that rise like terrestrial dust devils, twisting across plains in narrow spirals. These dust devils have been captured in images by orbiters and rovers, thin plumes dancing across the red ground. At times, however, storms grow far larger. Regional dust storms can cover vast areas, obscuring the landscape beneath hazy veils. And occasionally, once every few Martian years, a storm can expand to become global, enveloping nearly the entire planet in suspended dust. During such events, sunlight struggles to reach the surface. The sky grows darker. Solar-powered spacecraft must rely on stored energy as panels collect less light. These global storms are not violent in the sense of Earth's hurricanes. The wind speeds can be significant, but because the air is so thin, the force exerted on objects is less than one might expect. Instead, it is the dust itself that defines the storm, a fine, persistent haze that wraps the planet in muted amber. Clouds drift in higher altitudes, composed primarily of water ice. They form especially near volcanoes and in equatorial regions during certain seasons. There are also clouds of carbon dioxide ice that can appear in colder conditions. These clouds are delicate, thin streaks that soften the sky, sometimes glowing faintly in morning light. In winter near the poles, frost can settle onto the surface. Carbon dioxide from the atmosphere freezes directly into dry ice, forming seasonal caps that grow and shrink with the shifting seasons. In some areas, even water ice may deposit as frost, shimmering faintly before sublimating back into vapor as temperatures rise. Mars' axial tilt, similar to Earth's, ensures that seasons play an important role in its climate. But because its orbit is more elliptical, the southern hemisphere experiences more extreme seasonal variations. Southern summers occur when Mars is closer to the Sun, making them shorter and warmer. Southern winters, conversely, happen when Mars is farther from the Sun, making them longer and colder. The northern hemisphere experiences milder seasonal contrasts. All of this unfolds slowly. Winds rise, dust lifts, clouds form and fade. Temperatures climb gently during daylight and retreat sharply at night. Frost appears and vanishes. If you stood on the Martian surface during a calm day, you might see faint ripples of dust skimming across the ground. The sky would glow softly. There would be no scent of rain, no humidity in the air. Only dryness, profound and ancient dryness. And yet, even in its austerity, Mars has weather. Not lush or thunderous, but subtle. A world where storms whisper instead of roar, where frost forms silently in the coldest hours before dawn, where sunlight filters through dust in muted tones. It is a climate defined by restraint, measured, sparse, and patient. Beyond the thin veil of atmosphere, above the drifting dust and the towering volcanoes, two small companions circle Mars in steady silence. They are modest in size, irregular in shape, and yet they add another layer of quiet intrigue to this red world. Their names are Phobos and Deimos. The names come from ancient Greek mythology. Phobos and Deimos were the sons of Ares, the Greek counterpart of the Roman god Mars. Their names mean fear and terror. It is a poetic inheritance from a time when the red planet was associated with war and conflict. And yet, these two moons themselves are not fearsome. They are small, uneven bodies, more like captured asteroids than the grand, spherical moon that orbits Earth. Phobos, the larger of the two, measures about 22 kilometers across at its widest point. Deimos is even smaller, only about 12 kilometers wide. Neither moon is round. Instead, they resemble irregular, lumpy stones, often compared to potatoes in shape. Their surfaces are scarred with craters, evidence of countless impacts over time. Phobos orbits remarkably close to Mars, only about 6,000 kilometers above the planet's surface. That is far closer than our moon is to Earth. Because of this proximity, Phobos races across the Martian sky. It completes an orbit in just over 7.5 hours, meaning it rises in the west and sets in the east, crossing the sky more than once in a single Martian day. Imagine looking up and seeing a moon move noticeably within a few hours, drifting swiftly overhead. Deimos, in contrast, orbits farther out, about 23,000 kilometers from the surface, and takes about 30 hours to complete a circuit. It moves more slowly across the sky, appearing smaller and dimmer than Phobos. Scientists believe these moons may be captured asteroids from the outer regions of the solar system, drawn into Mars' gravitational embrace long ago. Their irregular shapes and composition support this idea. They lack the smooth, spherical form that typically results from a body large enough for gravity to mold it evenly. Instead, they remain rough and asymmetrical, as if shaped by chance and preserved by stillness. Phobos, though small, holds a dramatic future. Its orbit is gradually decaying. Tidal interactions between Mars and Phobos are causing the moon to spiral slowly inward. Each century, it moves a little closer to the planet. In perhaps 30 to 50 million years, a vast span of time from our perspective, Phobos may either break apart under tidal stresses or collide with Mars' surface. If it breaks apart, the debris could form a temporary ring around Mars, creating a delicate halo of dust and rock. If it collides, the impact would leave a significant mark upon the planet. Either outcome is distant, unfolding on geological timescales far beyond human lifetimes. For now, Phobos continues its rapid dance, casting fleeting shadows on the red ground below. Deimos appears more stable in its orbit, drifting quietly at a safer distance. It is smaller, less dramatic, but no less fascinating. Its gentle path around Mars is steady, predictable, unhurried. From the surface of Mars, these moons would appear different from our own. Phobos would loom larger in the sky than Deimos, but still much smaller than Earth's moon appears to us. Its irregular outline would be visible as it passed overhead. During certain alignments, it could eclipse the sun briefly, not completely, but partially, casting a small, swift shadow that glides across the dusty terrain. Imagine standing beneath that thin sky as Phobos crosses in front of the sun. The light dims slightly. A small, uneven silhouette moves across the solar disk. Then, just as quickly, the light returns to normal. A momentary celestial whisper. Together, Phobos and Deimos remind us that even small worlds can host companions. They are not grand or luminous, but they add rhythm to the Martian sky. They rise and set. They circle and recede. They carry ancient names rooted in myth, yet follow precise orbital paths defined by gravity. Two small stones in endless motion, one slowly drawing closer to its fate, the other circling at a quiet distance. Above the red plains and silent canyons, they continue their patient revolutions, modest guardians of a smaller world. If there is one question that has echoed most persistently around Mars, it is this: was there ever water here? Water is quiet, but transformative. On Earth, it carves valleys, fills oceans, shapes climate, and sustains life. So when we look at Mars and see dry riverbeds etched into its surface, we cannot help but pause. The shapes are unmistakable. Winding channels that branch and rejoin. Delta-like fans where sediments appear to have spread outward. Basins that resemble ancient lake beds. From orbit, some valleys look so similar to terrestrial river systems that it is difficult to imagine they were formed by anything else. Their curves are fluid, not jagged. They suggest flow, persistent directional movement across the land. These features point toward a distant past when Mars may have been warmer and wetter, when liquid water flowed across its surface for extended periods of time. In certain craters, especially those explored by robotic missions, scientists have identified layered sedimentary rocks. These layers resemble deposits formed in lakes on Earth. Fine particles settle slowly through calm water, accumulating in distinct bands over time. The presence of such formations suggests that stable bodies of water once existed, perhaps lakes that endured for thousands or even millions of years. And then there are minerals. Some minerals only form in the presence of water. Orbital spectrometers and rover instruments have detected clays and sulfates in Martian rocks, minerals that typically require water to form or alter existing material. Their presence strengthens the case that Mars once hosted liquid water on a significant scale. Yet today, liquid water is unstable at the surface. The thin atmosphere and low temperatures prevent it from lingering. Instead, water exists primarily as ice. At both poles, layered ice caps persist, composed of water ice and seasonal layers of frozen carbon dioxide. These polar caps grow and shrink with the seasons, breathing faintly in response to temperature shifts. Beneath the surface, radar data suggests the presence of subsurface ice deposits at various latitudes. In some regions, particularly near the poles, ice lies just beneath a thin layer of soil. In other areas, buried glaciers appear to be preserved under blankets of dust and debris, protected from direct sunlight. There have also been observations of dark streaks appearing seasonally along steep slopes, features known as recurring slope lineae or RSL. These streaks darken during warmer seasons and fade during colder ones. Initially, they were thought to be caused by transient flows of salty water. The salts would lower the freezing point, allowing briny liquid to exist briefly before evaporating or freezing again. However, more recent studies suggest that at least some of these streaks may instead be dry flows of granular material. The debate continues quietly as scientists analyze data and refine interpretations. I find it calming to imagine a time when Mars' northern lowlands may have hosted an ocean. Shallow perhaps, but expansive. Waves lapping gently under a pale Sunday clouds forming overhead. Rain falling lightly onto volcanic plains. It is speculative, yes, but grounded in geological evidence that water once moved freely. The question then becomes, where did it go? Some water likely escaped into space after the atmosphere thinned and solar wind stripped away protective layers. Some may remain locked in minerals or frozen underground. Over time, the planet cooled, and the conditions that once supported flowing rivers faded. And yet, even in its current state, water remains present, quiet, frozen, preserved in ice caps and buried deposits. It waits beneath the surface, layered in frost and dust. Mars today is dry and cold, but its rocks remember water. Its valleys remember water. Its minerals remember water. A world that once may have glistened briefly with rivers now rests in stillness, holding its frozen reserves in silence. As the evidence of ancient water settles quietly in our thoughts, another question rises, softer, but perhaps even more profound. If water once flowed across this world, could life have emerged there as well? The search for life on Mars has been careful, methodical, and patient. In the 1970s, the Viking missions became the first spacecraft to successfully land on the Martian surface and conduct experiments designed specifically to detect biological activity. Each Viking lander carried instruments that analyzed soil samples, searching for chemical reactions that might indicate the presence of microorganisms. Some of the results were intriguing. One experiment produced a chemical response that, at first glance, resembled metabolic activity. However, other supporting evidence was absent. Over time, scientists concluded that the reactions were likely caused by reactive chemicals in the soil rather than living organisms. The Viking findings remain a subject of reflection, a reminder that life detection is subtle and easily confounded by unfamiliar chemistry. Since then, the search has grown more refined. Rather than looking directly for living organisms, modern missions focus on identifying biosignatures, indirect evidence that life may have once existed. These include organic molecules, specific mineral patterns, and chemical imbalances that could suggest biological processes. The concept most often discussed is microbial life. Not cities or forests, but tiny, single-celled organisms, life forms similar to the earliest microbes on Earth. On our planet, such microorganisms thrive in extreme environments. Deep beneath the ocean floor, in acidic hot springs, in frozen Antarctic lakes. If life arose on Mars when it was warmer and wetter, it may have been similarly simple and resilient. One of the most intriguing findings in recent decades has been the detection of methane in the Martian atmosphere. Methane is a molecule that can be produced by biological processes, but it can also form through geological reactions. Observations from orbiters and rovers have detected small, fluctuating amounts of methane near the surface. The presence of methane is puzzling because sunlight and chemical reactions in the atmosphere should break it down relatively quickly. If methane is still being detected, something may be replenishing it. Is it geological activity beneath the surface? Perhaps water interacting with certain rocks? Or could it be microbial life hidden underground, slowly releasing methane as a byproduct? Present, there is no definitive answer. The methane detections remain subtle, variable, and sometimes difficult to confirm. Yet they continue to inspire investigation. Recent rover missions have focused on ancient lakebeds and sedimentary formations where life, if it ever existed, would have had the best chance to thrive. By drilling into rocks and analyzing their composition, these missions search for organic molecules, carbon-based compounds that are the building blocks of life. Some complex organic molecules have indeed been detected. However, organic molecules alone do not prove life. They can form through non-biological processes as well. The search, therefore, is cautious. Each piece of evidence is weighed carefully. Scientists look for patterns, context, and consistency. Life detection requires more than a single signal. It requires a convergence of clues. I find something deeply peaceful in this careful approach. There is no rush to declare discovery. Instead, there is patience, a willingness to gather data slowly, to let the evidence accumulate layer by layer, much like sediment settling in an ancient lake. Imagine a time billions of years ago when Mars had thicker air and flowing water. In shallow pools warmed by sunlight, simple chemistry may have unfolded. Molecules combining, separating, recombining. Perhaps in some sheltered niche, life briefly flickered into existence. Or perhaps it never did. The beauty of the question lies not only in the possibility of life, but in the act of searching. Robotic explorers traverse the surface methodically, sampling rocks, analyzing soil, listening for faint chemical whispers. They move slowly, deliberately, across landscapes shaped by ancient water. So far, no definitive proof of life has been found, but neither has the possibility been closed. Mars remains a question, open, patient, and waiting beneath its rust-colored sky. Long before we could see Mars in high resolution, before we could trace the curves of its valleys or measure the height of its volcanoes, we reached toward it with machines, small emissaries of metal and circuitry sent across the void. The story of exploration is itself a quiet testament to human patience. In the early 1960s, the first successful flyby missions passed near Mars. NASA's Mariner 4 in 1965 transmitted the first close-up images of another planet. The photographs were grainy by modern standards, narrow strips of cratered terrain printed in black and white. Yet they transformed our understanding. Mars did not appear lush or canal-laced as once imagined. It appeared cratered, stark, ancient. Later Mariner missions expanded this view, revealing vast volcanoes and immense canyon systems. These early flybys did not land. They merely passed by, collecting data and sending it home. But they marked a beginning. In the 1970s came the Viking missions, the first to successfully land and operate on the Martian surface. Each Viking spacecraft consisted of an orbiter and a lander. The orbiters mapped large portions of the planet from above, while the landers descended gently to the surface using parachutes and retrorockets. For the first time, we saw Mars from ground level, a rocky plain stretching toward a dusty horizon under a pale sky. The Viking landers conducted experiments, including the life detection tests we discussed earlier. Though conclusive evidence of life was not found, the missions proved that long-term surface exploration was possible. They operated for years, transmitting images and scientific data across millions of kilometers. After a quieter period, exploration resumed with renewed energy in the 1990s. The Mars Pathfinder mission, which landed in 1997, carried a small rover named Sojourner. It was modest in size, about the size of a microwave oven, yet it demonstrated that mobile exploration was feasible. Sojourner rolled slowly across the surface, analyzing rocks and soil. Its movements were cautious and deliberate, but symbolic. Mars was no longer a static photograph. It was a landscape to be traversed. In the 2000s, two larger rovers arrived, Spirit and Opportunity. These twin explorers landed on opposite sides of the planet in 2004. Originally designed to operate for 90 days, they far exceeded expectations. Spirit explored volcanic plains and evidence of past hydrothermal activity. Opportunity roamed for nearly 15 years, traveling more than 45 kilometers. A remarkable journey on another world. Along the way, Opportunity discovered minerals that strongly suggested ancient water. Then came Curiosity in 2012, a rover the size of a small car. It landed within Gale Crater, near the base of a mountain of layered sediments. Curiosity's mission has been to assess whether Mars ever had conditions suitable for life. It carries advanced instruments capable of analyzing rock chemistry and detecting organic molecules. As it climbs gradually up the slopes of Mount Sharp, It reads the geological record like pages in a book, each layer revealing clues about ancient climate shifts. In 2021, Perseverance arrived, landing in Jezero Crater, a site believed to have once hosted a river delta flowing into a lake. Perseverance's mission is not only to search for signs of ancient life, but also to collect and cache rock samples for eventual return to Earth. These samples, carefully sealed in tubes, may one day be brought back by future missions for detailed laboratory analysis. Orbiters continue to circle above. Spacecraft such as Mars Reconnaissance Orbiter, MAVEN, and others map the surface in extraordinary detail, study the atmosphere, and analyze the planet's magnetic remnants. From high above, they monitor dust storms, track seasonal changes, and guide rovers safely across the terrain. Exploration unfolds slowly. Each mission builds upon the last. Data accumulates. Maps grow sharper. Hypotheses refine. When I imagine these robotic explorers, I see them moving with patience across vast plains, their wheels leaving tracks that may remain visible for years in the undisturbed soil. They pause, extend robotic arms, drill gently into rock. They listen to the wind through microphones. They gaze at sunsets and transmit those images home. Through them, we have come to know Mars not as a distant dot, but as a textured, varied world. A planet explored step by step, orbit by orbit, quietly, methodically, persistently. In recent years, the story of Mars has continued to unfold, not in sudden revelations, but in careful, incremental discoveries that deepen our understanding layer by layer. Each new finding adds texture to a world that once seemed simple and barren. One of the most discussed discoveries has been the possible detection of subsurface lakes near the planet's south pole. Using radar instruments aboard orbiting spacecraft, scientists observed bright reflections beneath layers of ice. These reflections suggested the presence of liquid water trapped below the surface, insulated by thick ice above. The idea of liquid water existing today, even buried and isolated, is captivating. If confirmed, it would mean that Mars still harbors pockets where water remains stable, protected from the harsh surface environment. However, interpretation of the radar data is complex. Some researchers argue that the reflections could also be explained by certain types of mineral deposits. The debate continues gently, with new data analyzed carefully, conclusions weighed patiently. Meanwhile, the rover Curiosity has detected complex organic molecules within sedimentary rocks in Gale Crater. These molecules, composed of carbon and other elements, are building blocks that on Earth are often associated with life. Yet, as always, caution is essential. Organic molecules can form through non-biological processes as well. Their presence tells us that Mars possesses the chemical ingredients necessary for life, but not whether life ever used them. Still, their discovery is meaningful. It confirms that ancient Martian environments were chemically rich. In rocks that formed billions of years ago, preserved beneath layers of dust, there are traces of organic chemistry, quiet echoes of a more dynamic past. Perhaps one of the most poetic achievements in recent exploration was the flight of Ingenuity, a small robotic helicopter that accompanied the Perseverance rover. In 2021, Ingenuity became the first aircraft to achieve powered, controlled flight on another planet. Mars' thin atmosphere made this feat especially challenging. With air density less than 1% of Earth's, the helicopter's rotors had to spin extremely fast to generate enough lift. On its first flight, Ingenuity rose gently above the surface, hovered briefly, and then descended. The entire flight lasted less than a minute, but it marked a new chapter in planetary exploration. Subsequent flights demonstrated that aerial scouting could support surface missions, offering new perspectives and helping identify safe paths for rovers. Ingenuity's small shadow drifting across the Martian soil became a symbol, not of conquest, but of quiet ingenuity and persistence. Orbiters have also continued to refine our view of Mars. High-resolution cameras have revealed fine details, shifting sand dunes, seasonal changes in frost patterns, fresh impact craters appearing over time. These observations remind us that Mars, though ancient and still, is not entirely static. Its surface continues to evolve subtly. There have been detections of transient methane spikes in the atmosphere, measured both from orbit and at the surface. Though small and inconsistent, these signals renew questions about possible geological or biological sources. Each new measurement invites further scrutiny, deeper analysis. What strikes me most about these recent discoveries is their restraint. There are no dramatic transformations, no sudden bursts of revelation. Instead, there is refinement, an ever-sharper understanding of conditions past and present. We learn that beneath the polar ice, there may be hidden reservoirs, that within sedimentary rocks, organic molecules endure, that a tiny helicopter can lift itself into alien air, that dunes migrate slowly, grain by grain. Mars does not reveal itself all at once. It yields information gradually through careful observation and repeated measurement. And as these discoveries accumulate, the image of Mars grows more nuanced. Not merely a red desert, but a world layered with complexity, geological, chemical, atmospheric. A planet that still surprises, softly and methodically. As our understanding of Mars grows more detailed, another quiet question begins to form, not about what Mars was, but about what it might become. Could humans one day live there? And if so, what challenges would they face beneath that butterscotch sky? The first challenge is radiation. On Earth, we are protected by two powerful shields, a thick atmosphere and a global magnetic field. Mars has neither in comparable strength. Its atmosphere is thin, and its global magnetic field largely faded billions of years ago. As a result, cosmic rays from deep space and energetic particles from the Sun reach the surface more easily. Measurements taken by rovers have shown that radiation levels on Mars are significantly higher than those on Earth's surface. Prolonged exposure would increase health risks for astronauts. Any long-term settlement would require protective habitats, perhaps buried beneath regolith or constructed with materials capable of blocking radiation effectively. Even the soil itself could serve as shielding if used wisely. Then there is the soil's chemistry. Martian regolith contains perchlorates, salts that can be toxic to humans in high concentrations. These compounds can interfere with thyroid function and pose risks if inhaled or ingested. For future explorers, careful management of dust will be essential. Airlocks, filtration systems, and protective suits would be necessary to prevent contamination within habitats. The lower gravity presents another uncertainty. At 38% of Earth's gravity, Mars would exert less strain on the human body. While that might initially feel pleasant, easier movement, lighter steps, the long-term effects remain unclear. On the International Space Station, astronauts experience muscle and bone loss in microgravity. Mars' gravity is stronger than that of orbit, but still weaker than Earth's. Would extended stays lead to gradual weakening? How might the cardiovascular system adapt? These are questions that require study and cautious optimism. Temperature and climate also pose difficulties. Though equatorial regions can briefly warm during the day, nights remain deeply cold. Habitats would need reliable heating systems. Energy generation, perhaps through solar panels or nuclear reactors, would be essential. Dust storms, though not physically destructive in the way hurricanes are on Earth, could reduce sunlight for weeks, challenging solar power systems. Distance introduces psychological and logistical hurdles. When Mars and Earth are farthest apart, they can be separated by more than 400 million kilometers. Even at their closest approach, communication signals take several minutes to travel one way. This delay prevents real-time conversation. Astronauts on Mars would operate with a degree of autonomy never before required. Resupply missions would be infrequent and complex. Everything necessary for survival, air, water recycling systems, food production, would need to be either transported or generated locally. Scientists are exploring ways to extract water from subsurface ice, to produce oxygen from carbon dioxide, and to grow crops in controlled environments using Martian soil treated to remove harmful compounds. Isolation itself may be one of the most subtle challenges. A crew on Mars would see Earth as a small, distant star in the sky. The familiar blue sphere would shrink to a pale point of light. The sense of separation would be profound, beautiful perhaps, but also weighty. And yet, despite these challenges, Mars remains the most plausible destination for human exploration beyond Earth. This day length is similar to ours. Water exists in frozen form. This gravity, though lower, is not negligible. When I imagine a human habitat on Mars, I picture modest structures, perhaps domes or partially buried modules, glowing softly against the red landscape. Inside, controlled air, recycled water, small gardens illuminated by artificial light. Outside, the quiet expanse of dust and stone. Living on Mars would not be easy. It would require resilience, ingenuity, and constant awareness of environmental limits. But the challenges themselves are instructive. They remind us how delicately balanced Earth is, how our atmosphere, gravity, and magnetic field work together to sustain life effortlessly. Mars offers possibility, yes, but it also offers perspective. A world where survival would be intentional, engineered, and carefully maintained. A quiet frontier, waiting, not urgently, but patiently. As we consider the challenges of living on Mars, it feels only natural to wonder how humanity plans to approach such a distant endeavor. The vision of stepping onto that red soil is no longer confined to science fiction. It exists within carefully drafted proposals, long-term roadmaps, and evolving spacecraft designs. NASA has outlined ambitions that extend into the 2030s and 2040s. A gradual pathway that begins with robotic exploration, expands through lunar missions under the Artemis program, and ultimately prepares for crewed journeys to Mars. The Moon is seen as a proving ground, a place to test life support systems, habitat construction techniques, and sustainable operations beyond low Earth orbit. Lessons learned there would inform future missions to Mars. A crewed mission to Mars would be long, many months traveling through deep space, followed by time spent on the surface before a return journey. The total mission duration could approach 2 to 3 years. To sustain astronauts for such a period, spacecraft would need advanced recycling systems for air and water, radiation shielding, and reliable propulsion. Private companies have also articulated bold visions. SpaceX, for example, has proposed the development of Starship, a fully reusable spacecraft designed to carry large payloads and, eventually, human passengers to Mars. The concept envisions multiple starships launching during favorable planetary alignments, transporting equipment, supplies, and crews. The long-term idea extends beyond a single expedition. Some proposals imagine the gradual establishment of a permanent base, a small outpost that grows over time. Initial missions would focus on survival and scientific research. Later phases might explore in situ resource utilization, extracting water from ice deposits, producing methane fuel from atmospheric carbon dioxide, generating oxygen, and cultivating food in controlled greenhouses. In some visionary concepts, Mars becomes not just a research station but a settlement, a city beneath domes or within underground habitats carved into rock for radiation protection. These ideas remain distant and complex, requiring technological advances and sustained international cooperation. Yet they persist, quietly evolving in design studies and simulations. There is a certain calm determination in these plans. No immediate rush, no dramatic declarations of imminent departure. Instead, incremental progress, testing materials, refining engines, practicing autonomy in remote operations. Each advancement builds upon decades of research. International collaboration may play an essential role. Mars exploration is not solely the ambition of one nation or organization. Space agencies around the world contribute orbiters, instruments, and expertise. The shared pursuit of knowledge encourages partnership across borders. When I imagine the first human footprints on Mars, I do not envision triumphant shouts echoing across canyons. I picture something quieter, an astronaut stepping down carefully, boots pressing into fine dust. A brief pause, a look across the horizon, the sky pale and still. Perhaps the moment would feel contemplative, aware of the immense distance traveled, aware of the delicate systems sustaining life within the suit. The red soil beneath those boots would not be conquered, but encountered. The vision of Mars as a second planet for humanity remains distant. Earth remains our home, vibrant, alive, irreplaceable. Mars, by contrast, would require effort to become even marginally hospitable. Yet the aspiration to reach it reflects a broader human trait, the desire to explore, to extend our understanding, to see what lies beyond familiar boundaries. The plans are cautious, technical, and long-term. They speak of engineering challenges, funding realities, and patient development. Mars is not a destination for tomorrow. It is a horizon for decades to come. And as rockets are designed, habitats envisioned, and timelines refined, the red planet continues its steady orbit, waiting without urgency, turning beneath a smaller sun. Long before spacecraft ever traced careful arcs toward Mars, the red planet had already taken root in human imagination. It lived in stories, in sketches, in whispered speculations beneath starlit skies. Even without telescopes powerful enough to reveal its true surface, we projected meaning onto that distant ember. In literature, Mars became a stage upon which human hopes and anxieties played out. In 1898, H.G. Wells published The War of the Worlds, imagining Martians as technologically advanced beings invading Earth. His portrayal was not merely about aliens. It was a reflection of imperial tensions and scientific curiosity at the turn of the century. Mars became a mirror for humanity's own fears and ambitions. Edgar Rice Burroughs later created the Barsoom series, transporting readers to a romanticized Mars filled with strange creatures, ancient cities, and heroic adventures. In these stories, Mars was not barren and cold, but vibrant and populated. It was a canvas for imagination, shaped by limited scientific knowledge and boundless creativity. As astronomy advanced and robotic missions revealed a more desolate reality, Mars' role in fiction evolved. In modern film, it often appears as a place of survival and resilience. Movies like The Martian portray astronauts stranded on its surface, relying on ingenuity and science to endure. The Red Planet becomes less a realm of alien civilizations and more a test of human adaptability. Other films, such as Total Recall and Mission to Mars, weave narratives of mystery and exploration. They speculate about hidden artifacts, ancient secrets, or transformative discoveries. Even when exaggerated, these portrayals reflect enduring fascination. Mars is rarely just a backdrop. It is central to the narrative, a character in its own right. Beyond books and cinema, Mars has influenced music and video games. It appears in song lyrics as a symbol of distance and longing. It serves as a setting for digital worlds where players explore, colonize, or survive. In these mediums, Mars shifts shape easily, from hostile frontier to terraformed paradise. What I find most gentle about Mars' presence in culture is how it evolves with knowledge. When we knew little, it was a world of canals and civilizations. When we learned more, it became a silent desert. And now, as exploration continues, it stands somewhere between realism and aspiration, grounded in science yet open to possibility. Even children's drawings often include a red planet with two small moons nearby. The image has become familiar, recognizable, a symbol of curiosity itself. And perhaps that is Mars' greatest cultural contribution. Not fear, not fantasy, but inspiration. It encourages questions. It invites speculation. It reminds us that the night sky is not static, but filled with worlds. When we look up and see that steady red light, we carry centuries of storytelling with us. Mythology, science fiction, scientific discovery. Each layer adds depth to the simple act of observing a planet across space. Mars, in culture, is not only a place. It is a possibility, a metaphor for distance overcome, a symbol of exploration. And as we drift gently toward our final reflections, that small red glow remains, not only in telescopes and spacecraft data, but in imagination. A world that has shaped stories as much as science. As we arrive at the quiet edge of our journey, Mars no longer feels like a distant point of light, but like a world layered with memory, geological memory, atmospheric memory, even cultural memory. It is smaller than Earth, colder, thinner in air, yet vast in significance. Scientifically, Mars serves as a laboratory of planetary evolution. It teaches us how worlds form, how atmospheres change, how magnetic fields fade, how water can vanish from a surface yet remain preserved in ice and stone. By studying Mars, we gain perspective on Earth, on the delicate balance that sustains oceans, forests, and life. The valleys carved by ancient water remind us that climates can shift dramatically over time. The towering volcanoes speak of internal heat that once surged more actively. The canyon systems record tectonic tension released long ago. Even the thin atmosphere, fragile and restless, tells a story of gradual loss under the influence of solar wind. Mars is not simply an object of curiosity. It is a chapter in the broader narrative of our solar system. By examining its rocks and sediments, we peer backward billions of years, glimpsing conditions that may once have resembled early Earth. And then there is the question of potential. Could Mars become a second home for humanity? Perhaps one day, small settlements will exist beneath protective domes or within sheltered caverns. Perhaps children will grow up knowing two horizons, one blue, one red. Yet even if that future remains distant, the aspiration itself carries meaning. Mars challenges us to think long-term, to consider sustainability, to recognize how extraordinary Earth truly is. It is easier to appreciate breathable air, flowing water, and protective magnetic shielding when imagining their absence. But Mars also invites humility. It reminds us that planets endure beyond human timelines. Olympus Mons rose over millions of years. Valles Marineris fractured slowly. Ice caps grew and retreated with the rhythm of seasons stretching across centuries. Even if humans eventually walk its plains, Mars will remain older than our footprints. It will continue its orbit, sol after sol, year after year, indifferent yet quietly magnificent. As we reflect, the red planet becomes less a target and more a companion, a neighbor whose story intersects with ours. Through robotic explorers and telescopic observations, we have begun to know it not as myth, but as place. Its importance lies not only in whether we settle there, nor solely in whether life once flickered beneath its sky. Its importance lies in what it reveals about possibility and change, about fragility and resilience, about curiosity as a driving force. The small red ember that ancient astronomers watched with wonder now carries a wealth of data, images, and carefully collected samples. Yet its mystery is not exhausted. There are still layers beneath the surface, chemical questions unresolved, historical details waiting to be uncovered. Mars turns steadily in the dark, carrying its frozen poles, its silent dunes, its circling moons. And as we conclude, it stands as both destination and mirror, a world that helps us understand not only the cosmos, but ourselves. Now, let us allow everything to soften. The red deserts fade gently in your mind. The towering volcano becomes a silhouette against a dim horizon. The canyons grow quieter, their shadows blending into dusk. The thin atmosphere drifts in pale layers above the plains. Imagine Mars receding slowly into the distance, returning to its place among the stars. A small, steady glow against velvet darkness. No urgency, no noise, only motion, calm, predictable motion. Wherever you are tonight, perhaps the sky above you holds that same faint red light. Perhaps it is hidden by clouds or resting beyond the horizon. Even so, it remains there, orbiting, turning, enduring. Let the scale of it all settle gently within you. The vast distances, the long years, the patient accumulation of dust and stone. Breathe slowly. Feel the quiet continuity of planets moving in their paths. Mars will continue its journey whether we watch or not. But tonight, for a little while, we have watched together.